Okay, good morning, everyone. It's my pleasure to introduce Ömer Güneş as our speaker today. So let me just briefly introduce him to you. Dr. Güneş got his PhD degree from the Department of Computer Science at the University of Oxford, and he is now a postdoctoral researcher there. And currently he is working on automated knowledge-based construction, specifically to its applications to scientific documents, and also ethical aspects of dialogue systems. He is also leading the NLP team at DeepZen, where he pursues his research on emotion recognition, character identification, language modeling, conversational AI, and multimodal machine learning. And today he will talk about their efforts on deep learning-based approaches to character identification from narrative text. Thank you, Ömer Hocam. The stage is yours.
Thanks a lot. It's a real pleasure to address such a privileged audience. And actually, before starting, I think I have to share a story from yesterday. Actually, we're trying to organize a competition on Turkish NLP, and I was planning to follow up with Deniz Hoca regarding that, actually. And yesterday, we were trying to finalize the themes, like what sort of topics that we were gonna propose. And one of the committee members just proposed character recognition. And then I just realized that, oh, maybe the audience might be a bit confused, like when I state the title as character identification, because the committee member yesterday just proposed optical character recognition, OCR. So that's just one sort of problem related to characters. And also there are some other character-related problems as well, but I will explain in detail what I mean by character identification throughout this talk. So this is a joint work with Furkan Kadıoğlu, Şükrü Bezen, Christophe Veu, and Ranieri Maya from DeepZen. Before getting into details, I would like to share 4 definitions. Those definitions are key because we designed several of the components in the pipeline according to those definitions. First of all, a character is an animate being that is important to the plot. That's a definition that we took from Jehan's 2020 paper on the same problem. And secondly, for the people who are out of NLP world, we're working on coreference resolution. And a coreference occurs when 2 or more expressions in a text refer to the same person or thing. In other words, like they have the same referent, and then they constitute a character chain. Let me read this sample sentence. This is part of a sample text passage that I'll use throughout this presentation. So it's just one sentence consisting of 2 quotations and a narration. It starts with a quotation saying that my dear Mr. Bennet said his lady to him one day, have you heard that Netherfield Park is let at last? So from the initial quotation, we can understand that, actually from the narration, we can understand that a woman is uttering it. And from the utterance, we can understand that she is addressing a man. And then in the narration part again, she is referring to this same person as well. So from just the initial utterance and the narration part, we can locate 2 references. And those 2 references are corresponding to the same character. Here, like from the context, we can infer that the name for this character is Mr. Bennet. But the key thing here is to identify the characters, not to name them. And the third definition is a quotation. It's a group of words taken from a text or speech and repeated by someone other than the original author. And related to that, a dialogue is the exchange of spoken words between 2 or more characters in a book, play, or other written work. And the dialogue is a set of quotations and narrations. That's the reason why in the title we said a narrative text. We have a sample dialogue. Again, it's starting with a quotation. Do not you want to know who has taken it? It is colored as red because it's spoken by character 1, and then the narration which says, cried his wife impatiently. And then there's a turn here in the dialogue. The second character is uttering, you want to tell me, and I have no objection to hearing it. So that's one of the sample dialogues that we will see, that kind of dialogues throughout the talk quite frequently. And this is a big picture of the character identification pipeline that we propose. It has 6 key components. Given a book as input, or in other words, a long form document, a document on average containing 300 pages or 60,000 words or tokens, the goal is to generate a list of characters from the input, and then a list of quotations, and finally to map those characters and quotations so that we can, as an output of this component, we can produce an enriched book so that this component, speech synthesis component, can generate a multi-voice, synthetically generated audiobook at scale. So that's the whole motivation. And before going into details of each component, I just want to run how it works through a sample text passage. So this is a text passage consisting of 6 paragraphs or sentences. And the first one is a mixture of utterances and narrations. I will gonna read the first part just to show you how we locate the correct coreference chains. So the same sentence, my dear Mr. Bennett said his lady to him one day. So this is an entity mention here, another entity mention, and they refer to the same character, so they're member of the same coreference chain. Have you heard that Netherfield Park is let at last? So the lady is addressing the same person again. In the second sentence, it's a narration. Mr. Bennett replied that he had not. There are 2 entity mentions, as you can see. Still, it's going on, but it is, returned she. Here, it is referring to this park. She refers to the lady who is saying that. For Mrs. Long has just been here and she told me all about it. So as we can see, there is no reference to the character 1. And in the first sentence, Mr. Bennett made no answer, another reference. Do not you want to know who has taken it? Cried his wife impatiently. Just one reference here. You want to tell me, and I have no objection to hearing it. There's one last. This is the whole set of coreference chain for character 1 in this setting. And this is the whole set of coreference chains for the second character. Sorry, this is the second coreference chain. I have to stop myself. This is the third coreference chain, which stands for the park and 2 other pronouns that refer to it. And lastly, this is the fourth coreference chain, which stands for another lady, and she only has 2 mentions in the third sentence. So the key thing is those are the all coreference chains. However, all of them are not representing characters in this setting. So we need to filter out the Netherfield Park, because according to the definition I gave in the first slide, it's not an animate object, so we need to filter out them, and that's character mining which does it. So it sort of extracts character chains from coreference chains. That's how it works. Quotation extraction is the other component. It seems pretty straightforward to extract quotations from text. Like you can use some regex expressions, or like it's mostly like you can develop a simple feature-based machine learning classifier to do that as well. However, so those are the quotations in the text, and there are different patterns actually. So the first and third sentence are consisting of two utterances, two quotations and a narration in the middle. The fifth one is a mixture of quotation and afterwards narration, and the last one, the whole sentence stands for quotation. However, there are more challenging situations, such as this one, which is an indirect, which includes an indirect quotation. So the offices will be staffed by employees who will bring specific expertise in their country's banking system to each marketplace, the company said. So we also need to extract those sort of quotations from the text in an automatic fashion. Another example is mixed quotations. A stock exchange of Singapore spokesman said the company had requested for the suspension pending an announcement soon. Even this is more challenging, so we need to, or this is at the same level of difficulty, we need to extract those this quotation as well. There are more challenging examples from O'Keefe's 2012 paper, and we cover all those kind of quotation extraction problems up to a certain level in our current implementation. Another component is dialog detection. It captures the dialog boundaries and dialog terms. This is also key for us. The first thing is dialog boundary detection, which captures the first and last quotations in dialog. Again, if I refer back to the definition at the beginning, a dialog is a mixture of quotations and narration part. So this passage starts with narration, and until the first quotation here, there is no dialogue, as we can see. This is the beginning of the dialogue. And then the next task is to detect the turns in the dialogue, which is called the dialog turn detection problem. It captures the quotation which causes speaker changes in the dialogue. So again, there are four paragraphs here, and the first paragraph is just an utterance, which corresponds to just one speaker. And as we can read it, as we can see from the context, someone is addressing Mr. Bennett, a person, saying that, my dear Mr. Bennett, and it continues like that. In the second paragraph, it is starting with another quotation saying that, now, Kitty, you may cough as much as you choose, said Mr. Bennett. Oh, that's interesting, right? So the person who is uttering this quotation has been referred in the previous quotation. So there should be some change in the turn. Then this should be some part that is representing a turn in the dialogue. And then let's continue. Said Mr. Bennett, and as he spoke, he left the room, fatigued with the raptures of his wife. The third one, what an excellent father you have, girls, said she. Oh, another thing, like according to the change in the pronouns gender, let's say, we can detect another change here and locate it. Said she, when the door was shut. I don't know how you will ever make him amends for his kindness. So it seems like she's continuing the dialogue herself till end of this passage. And at the last part of this paragraph, she is mentioning Lydia, another person. My love, thought you are the youngest, and I dare say Mr. Bingley, another person who is being referred, will dance with you at the next ball. So the third turn has started here and it continues. Let's see if it will change in the fourth paragraph or not. Oh, said Lydia. All right, so then there's another change because this utterance is made by Lydia. So the whole setting, like this is the part that the turn changes. Oh, said Lydia stoutly, I'm not afraid, for though I'm the youngest, I'm the tallest. So that's potentially the part which is dialogue changing again. So that's the dialogue detection problem. I need to emphasize one thing at this point. At the dialogue turn detection, we are not detecting or recognizing which part is uttered by which character. You're just trying to detect the changes in the terms. Because this will be done by quotation attribution, which is the next thing. And it is being fed by the output of character mining, quotation extraction, and the dialog detection. So that's the output of character mining, all the character chains, all the quotations, and all the changes for the dialogues. Then the goal is to locate a quotation and map it to a specific character. So until the end of this passage, all those utterances are made by the same character according to quotation attribution component. And then the last part is uttered by another character. That's how it works. And also we need to locate the narrations as well, because in the ultimate, like our ultimate goal is to plug another voice and narrator voice to make it more natural. This continues like that, and that's it. All right, the first component that I want to share the details is reference resolver. In the past 5 years, obviously there's a huge development in the world of coreference resolvers. And initially we started with Manning's implementation, and I think that's part of the Spaces library at the moment. And then we just realized that it's not performing that well, so that we took a look at Lee's 2017 paper. He's one of the authors of the BERT approach, by the way. And then there are, like, obviously there are new approaches such as span BERT and incremental neural coreference resolution. That's also one another thing that we're working on. And lastly, we're working on learning to ignore, because we're working on long form documents. At some point, we need to ignore the history for the sake of efficiency. But in this one, I want to share with you, like, because it's part of our implementation, I want to share with you the details of the end-to-end neural coreference resolution approach. So, given a document D containing T words, first we're computing the total number of potential spans, which is T times T plus 1 over T. And for each potential span, they are just ordered by the start index, which is start of I. And then if they share the same start index, they're sorted according to the end index, end of I. And then the goal is to assign each span I an antecedent yi. Yi is a set of, as I said, potential assignments. It has epsilon, which is corresponding to dummy antecedent and all the rest for the true antecedent. An assignment is a dummy antecedent if J is not an entity mention, or I is not an entity mention, or lastly, there is no link between I and J. In other words, they are not sharing the same coreference chain. That's the case where we assign epsilon. In the other cases, we just assign the score for the span J. And the model is to learn the multinomial probability distribution of Y, as you can see from the formula. I think here the key thing is the scoring function. In the case of J is equal to epsilon, it's 0, and in other cases, it's the summation of mention score of I plus mention score of J, and also the antecedent score of the pairwise score of I and J. This is the architecture, the end-to-end architecture. In this case, the GI represents the spans, the vector representations for each possible span I. And the way that we compute the scoring function of I and scoring the dimension score of I and the antecedent score of I and J, which is the dot product of this vector representation with the weights. So here the key thing is two types of information are crucial. The context surrounding the dimension span and the internal structure within the span. And BiLSTMs are using to encode the lexical information on both the inside and the outside of each span. And lastly, just to compete with Manning's 2016 paper, they also propose an attention mechanism over words in each span to model the head words. And the advantage of this approach is they are not dependent on syntactic parsing. So that's how they claim, and the results seems like significantly better than, again, Manning's approach. And lastly, at the bottom, this vector is the representation for fixed pre-trained word embeddings, and also they use one-dimensional character embeddings, in which they are using the convolutional neural networks. Those are the formulas how they compute the representation score for spans. Yeah, I want to share the details of this approach. So given three potential spans, General Electric, the postal service, the company. By the way, in theory, there is no limitation on the length of the span. They're computing different scores, like the mention score for each span, and then the antecedent scores for the pairwise scores, such as the pairwise scores for the postal service and the company, or the General Electric and the company itself. And then they compute the coreference scores, which is a summation of the antecedent scores and the span representations, as can be seen in this formula. And finally, they do softmax, they do the ranking, and they pick the, in practice, they pick the best performing certain number of spans. The reason for it is, so if a document contains T words, like the full model described above, its complexity is like pretty high. And for this reason, they apply several pruning to increase the computational efficiency. Like first of all, they just choose the spans with up to L words, and only they compute their unary mention scores. And then they further reduce the number of spans to consider, like they keep only lambda times T spans with the highest mention scores. And also they filter out the cut off the K antecedents just to increase the efficiency more. It doesn't affect that much according to their score. So, and also in our implementation, for the value of 0.4 to lambda, like they can still keep the 92% of recall of their gold mentions. So in the final case, at the final step, they do the clustering produced by the most likely configuration. And that's how they do learning from the gold data. Here, gold I is representing this set of spans in the gold cluster containing span I. And then if span I does not belong to a gold cluster, all the gold antecedents have been pruned and they assign the epsilon value to gold of I. Like in summary, the model can quickly leverage this learning signal. And we also experience the same thing, so it learns pretty fast. When it comes to scores, that was the initial one that we designed our approach. And as I said, that's part of the SPACES neural network architecture. In our character identification pipeline, we've received almost similar, like in parallel to this one, we received significantly better performance or accuracy in the results. So in all, that's based on the Canal 2012 benchmark, and they are applying 3 different metrics, and on average, like they're at least 3% better than the second approach, which is good. But again, I have to say that like there's Spanbird or the most recent one, which is Learning to Ignore. So those scores are better, but that's where we are at the moment. Another thing is obviously those aspects matter in the sense that the distance and width features affect a lot, and also the like which embeddings you're using, or if you're using word embeddings or not, affects a lot. And then the other thing is how to use the speaker and genre metadata. This is also key to our case because we can extract the genre and style of the long form documents our own as well. The character embeddings, head finding, attention, and Turing embeddings are the other aspects that matter. That was the first component. The second component is character mining, which takes as input the output of the neural core resolver that I mentioned. The character mining outputs the character chains. Before going into details, like we are introducing 2 new metrics that we have to devise our own. The reason is like that makes it possible to get a more meaningful analysis when it comes to error analysis. So purity stands for how pure is the cluster, such as if we would have 3 character clusters, like let's say character 1 and the corresponding mentions, such as Mr. Bennett, Alexander Bennett, or him, or he, or many other instances of the same set. So here 75% shows, this is just a sample, that 75% of the mentions in this cluster is corresponding to same character, and the rest are corresponding to other clusters, so on and so forth. Here we use the harmonic mean of those 3 clusters. And also another thing is distribution, which means in a specific cluster, how many instances from, like, how many character instances are occurring, such as in the first cluster, if we have instances from 2 characters, then the entity, the distribution is 50%, so on and so forth. So, and then we use the arithmetic mean of those 3 clusters again. In the character mining stuff, like we have a pipeline of named entity recognizers, and then we do voting to filter the common person entities out of that. Here, obviously, we're not the first approach to do character mining. We like part of our implementation is based on Arduino's 2014 paper, but it's also beyond that. So in reconciling those outcomes of the entity recognizers, we're proposing a voting mechanism, and then we merge them with the outcome of the regex patterns. Then we, on this merged list, we apply clustering rules. So in this context, clustering is operation that puts all the references that belong to one character into one cluster. And I want to show a few examples why we need, like, opposite to the coreference resolution approach, why in this case we need a rule-based approach as part of the solution. Because we have quite a few examples like that, such as Miss Elizabeth Bennet and Elizabeth Bennet are 2 different references, and they're referring to the same person. So we need to detect those kind of expressions easily using several rules. So it's like first and last name similarities, for example. Again, another example, the abbreviations, they belong to the same person, or a hypochoristic, we apply a hypochoristic rule just to detect what are the different ways to write the same name, so on and so forth. And they, as you might imagine, they drastically affects the accuracy. Those are the scores. We have evaluated them on quarterly 3 dataset. I have to say, like, we're having competitive scores. We are very close to, and in some cases better, we were getting the best scores. But I have to say, like, there is a problem in the annotated dataset. So we had a series of sessions like how to, like, just to detect the wrong annotations in the dataset. So part of our future work is either extend the existing dataset or just to start from scratch, because this is a unique problem. It's not easy. It has different dynamics than other downstream NLP tasks. So we need to to claim something reliable. We need to focus on the dataset part, we believe. In the quotation extraction part, it's pretty straightforward, and we are having quite high scores, as you might imagine, but still we're dealing with these challenging tasks, and it's going better and better in each iteration. In the quotation attribution part, again, this is part of Musni's 2017 approach, but we're extending that. So the thing is, given a text document, a character list, and quotations, initially, we convert them into a spicy document, and in parallel, we're running them through a different set of neural core solutions or approaches, as I said. And the initial 7 approach that we showed at the beginning are the reference approaches for us. So they generate co-reference chains and fed into mentioned speaker, and this space document is fed into code to mention. And then code dimension is also, it is given as input the common speech verbs. To do that, we are maintaining a knowledge base for all the speech verb acts in a specific language. At the moment, it's English, but we designed it in a way to cover multilingual, like the other languages as well. Like, maybe you can question if the speech verbs are a finite set or not. They seem to be a finite set, but still we need to manage it or curate it, because some new ways of explaining speech might emerge, and we need to detect them and update this knowledge base accordingly. This is the same case. Like, this is just an instance of an ontology in which we represent the family relations. How, like, the family relations in the world are a finite set, but first of all, we need to propose a multilingual approach, so that we need to have a, like, instead of just keeping lists, we need to maintain a knowledge base. Secondly, like, the language evolves, and there are always different ways of explaining relations or speech, especially in the internet language or the slang language, so we need to be aware of them as well. That's the reason why we keep those knowledge bases, and the outputs are given into code to mention and mention to the speaker. Let me show you on a simple example how code to mention works. So we're proposing a set of rules according to, like, to implement a trigram mature, and it has several patterns, such as code verb mention verb code, and verb mention code. So it's like a window, and it detects throughout text any expression that fits into this, such as this is a code verb mention expression, and we detect them. In the next step, we need to find the speaker for the mention by utilizing co-reference chains. So this is the whole motivation why, as part of the pipeline, we use co-reference chains to resolve what does his mention mean in this context. So we visit the context, and we understand that it's Mrs. Bennett, so that we can resolve it. That's the accuracy on quotation attribution. So I have to say, those are the accuracies on separate components itself, and then we also measure the accuracy of the whole system, just to be sure how it performs. And the next thing is, I think, I just want to show you how it works in practice. So this is the same example that I showed. I will show 2 slides on that. This is the first part.
My dear Mr. Bennett,
said his lady to him one day,
have you heard that Netherfield Park is let at last?
Mr. Bennett replied that he had not.
But it is,
Returned she.
for Mrs. Long has just been here, and she told me all about it.
Mr. Bennett made no answer.
Do not you want to know who has taken it?
Cried his wife impatiently.
You want to tell me, and I have no objection to hearing it.
So in this case, the character identifier pipeline identifies 2 characters and assigns the relevant quotations to those characters. And then speech synthesizer just maps or plugs a specific voice to the character itself, and then the narration, the narrator, and the other character. Let me play the second one, and then I want to explain further our plans on that. And also I have to say that this is a non-edited speech. So normally when we produce a speech, we do post-processing to improve the quality, but I didn't want to do that, just to show you like what sort, like this is the outcome of character identification pipeline, like end to end. What is the given input and what is the output from the speech synthesizer, excluding the post-processing.
This was invitation enough.
Why, my dear, you must know, Mrs. Long says that Netherfield is taken by a young man of large fortune from the north of England, that he came down on Monday in a chaise and four to see the place, and was so much delighted with it that he agreed with Mr. Morris immediately, that he is to take possession before Michaelmas, and some of his servants are to be in the house by the end of next week.
What is his name?
Bingley.
Is he married or single?
Oh, single, my dear, to be sure, a single man of large fortune, 4,000 or 5,000 a year. What a fine thing for our girls.
How so? How can it affect them?
My dear Mr. Bennet,
replied his wife.
How can you be so tiresome? You must know that I am thinking of his marrying one of them.
So there are a couple of other things as well that we do just to increase the quality of the audio. Maybe I can talk them later, but just to say, such as we're detecting those speech verbs, like we also feedback the speech synthesizers, like on what sort of action it is to increase the quality.
This was invitation.
Sorry, that was the end. So in conclusion, like I think in less than we've been working for 4 years on the theory, but like practically in less than 1.5 years, we managed to develop an end-to-end character identification approach on narrative texts. Obviously, like we're actively working on the the most recent and shortlisted 7 approaches on neural coreference resolvers. Like in the future, we might focus on developing our own approach from scratch, but also another thing is we're sort of extending the existing approaches substantially. But again, like even the long-form texts in the recent neural coref papers that they mention are not long enough for our case. So we're really working on longer text. So efficiency is a key performance issue for us. So maybe we will focus more on the increasing the inference on coref resolution. So far, we've received the best results in character mining, but I need to emphasize that again, the data set is the bottleneck. Like I'm happy to share that we're getting the best results, but it should be something reliable, and we're working on increasing the amount of annotated data in parallel. So we just designed a new way to annotate those data, because it requires for an annotator to read the whole chapter or the whole book to understand how many characters there are and what are the relations between those characters. Another thing is we're getting the state-of-the-art results in dialog extraction. These boundary detection and turn detection problems are not as easy as in other cases, such as there's Ubuntu or daily dialog test cases, and they're just full of dialog terms. But in our case, like, it is mixed with narration, so we also need to count the narration in the model as well. The quotation attribution thing, like to map the quotations to characters, is one of the preliminary work in the literature. So we haven't seen, like, there are some there are approaches that extract characters, there are approaches that extract dialogue parts, but there is not any, like, we haven't seen so many approaches on how to cluster or map those two yet. So that's the reason why it's a preliminary work. And also we managed to produce the first synthetically generated multi-voice audiobook. I wish I could show you a better quality audiobook, a better quality audio sample, but again, it's pretty possible using our technology. As future work, obviously, like one of our key priorities is to propose a multilingual approach to all of the components, like to coreference resolver, character mining, especially quotation extractor, dialog extraction, and the quotation attribution part. And then we're planning to slightly extend the definition of the concept of character, because I think we discussed it with Deniz previously. So one problem is, if we assume that all the characters are animate objects, then we might miss several characters that are not functional but also has some roles. Like, they're not animate, but they have some roles to as part of the context, as part of the book. And I think that's something against, like, ignoring them is something against understanding those, understanding the content or understanding the document properly. So that's one of our plans. We're actively working on multimodal approaches to character identification. I'm not sure, but maybe some of you are working on video story understanding. So there's a drama QA dataset that we've discovered recently. So that's part of our work as well, like to leverage multi-modalities in order to improve the quality, not only for character identification, but also for emotion recognition, which is another thing that we're working on. Another thing is to propose a joint approach which with speech to text affect the quality of the audio as well. We had the early results of the experiments, and it seems like a new direction for us. So we will invest into this as well. And lastly, like, it's not the only problem of extracting, like, identifying the different characters in a given text, but also we need to understand the document better to extract the key aspects of those characters, like the personalities of those characters, to reflect, like, not only for speech synthesis, like, it has a direct impact into the speech synthesis, there is no doubt, but also, like, to represent the document, like, especially the semantics of the dialogues better. There are quite a few new data sets we've recently discovered on that, and we're hopeful. I think that's all from my side. Thanks for listening, and I'm happy to be in touch for further questions or in any collaboration.
Thank you, Ömer Hocam. So we are open to questions from our audience.
I hope
So maybe,
it wasn't.
So, Ömer, so let me start by asking. So we actually have a group that is trying to look into deeper story understanding problems. The motivation is not just to understand the story more, to generate higher quality text-to-speech, but that's a nice application. We want to sort of see if we can understand different aspects of stories at a deeper level. So having listened to your last two talks, it strikes me that, for example, the domain of emotions and tracking characters and their emotions, throughout a story would be a very nice problem to attack. What I have in mind is basically, pick these different domains, physical domain, emotional domain, social domain, etc. I remember a paper from a few years ago where they were tracking friends and foes, so social relations between these characters, etc. So I think there's a lot of different extensions of your work that can go into these directions that may or may not be relevant to speech production, but is definitely relevant to sort of deeper understanding of these stories beyond, what GPT-3 like models can do. So would you like to comment on sort of what other future work you see as a continuation of this?
Well, I think that's a very good point. Even we recently make a roadmap plan on how to synthetically generate text and also to bind it with, like at the moment we're working on audio related stuff. And to do that, as you mentioned, like first of all, there's a problem here. Like as we're working on emotion recognition and we hit the limits on emotion recognition from text, we need to have more multimodal approaches. So that's where we are. Like we sort of, I can say, almost covering all the data sets in multimodal context. And our early results of our experiments show that even for this problem of emotion recognition, the scores are much higher because it's not easy to detect the emotion of a phrase only from text. When you bundle it with not only like either audio features or visual features or all of them, obviously it depends on the computational efficiency. Like it's much higher. So we can like the key thing, the first thing that we can do is to disambiguate the senses of emotions, and also there are quite a few other features such as the pauses or the intensity of the. Again, I'm talking about in the context of speech synthesis, but those are transferable features to the domain. Other than that, like recently, we have just realized that what we're doing is still like it's not that tapped. Like we're just identifying the characters, and we need to understand the relations between those characters. When someone is referring to another person, like what is the relation between them? What are the actions between them? So to do that, we need to have either abstract meaning representation or similar document understanding approaches. Another thing is,
I mean,
again,
let me object to you there. So abstract meaning representation is some, human invented graph representation of the semantics of sentences. So I think the types of things you're talking about, long-term relationships between characters, goes way beyond that. So it's not, these things are not usually expressed in single sentences, but they evolve over, paragraphs and sections of text. So I don't think abstract meaning representation or any formal such, sentence meaning representation system is going to be sufficient to represent those. I'm not I don't know what the right answer is, how to represent those things, but it's not with abstract meaning representation. I can assure you of that.
Let me share you one example. There are some recent approaches on document representations, and their performance scores are a bit better than AMR. And also, let me share with you an exact problem that we are working on. In a given book, such as in the first chapter, there are several characters, but then throughout the book, they disappear. And towards to the end, they appear again. So we need to ask why it happens, how to track the occurrences of these characters. What happened throughout the book? What was the story? And so that they disappeared and they appeared again. Or I can say a few other examples as well. Those are the scenarios that we're facing. Again, it's not only for some product-related goals. It's really crucial to represent them in a way that we can be better aware of the way that we are handling the characters. That's key to us. And also, there is hypothetical concepts not even humans or not even creatures. So how to represent them? What are their impact to the character? Or what is the how to represent the inner world of a character? That's another problem.
Yep.
So they all comes to the semantic parsing or semantic representation of, in my opinion, and maybe you don't agree, but semantic representation of the document. I'm not only saying textual semantic representations, but again,
I agree with you in general that it has to be some sort of semantic representation. I just don't agree that human design graphical representations are going to cut it. It's probably going to be a mixture of those and the sort of distributed representations that you find in deep nets. But that's an empirical question that we need to, I guess, pursue and see.
I think another key thing is the learning mechanism. So how to learn, learning by experience, and how to reflect it in the scenario. So given, let's say, so one thing that we're trying to do is to realize the multimodal approach, such as we feed the system with YouTube videos. So these are long form video, longer videos, not short clips. And we're trying to analyze the dialogue part, the audio, and the alignment of the visual expressions. But as they are not active, I have doubts if they are enough to learn the experience so that it can be reflected into the understanding of the whole concept. I think also another thing, the last comment is, we're talking about, we're trying to process fiction books. So those are books that have a series of events in it. And it's how to say, to detect those events is also another key aspect, in my opinion. So it's sort of like building I hesitate to use the concept of knowledge base, but I think constructing an active knowledge base and to do reasoning on this knowledge base is I think part of the ideal pipeline, in my opinion. Yeah, but we're still at the early stages, I have to say. So there are too many things to do. It mostly depends on the data and the computing power and the approaches. Yeah, but
I think it's exciting. It's a very open field, and there's a lot of problems to focus on. So I want to end with you're welcome to join the next meeting with Aykut Hoca and our students of this story understanding group, and maybe we can discuss some of these future problems and which ones our students can tackle, and and we can collaborate on the general theme being, can we understand stories at a deeper level, but the specific problems we can choose to work on can be chosen based on the available data and feasible models right now.
That's what I was going to say. I before I made a quick survey, and I've been amazed with the abundance of the data sets, in especially story, video story understanding. Obviously, like, I think it might be helpful when it comes to processing transcripts or text, but again, also for the multimodal stuff as well. Yeah, that would be great. It would be delightful. Yeah, we have also some other plans. Maybe like we can talk later how to follow up further. So those are the exciting problems that we're busy with at the moment. And I have Furkan that we developed this work together in this meeting as well. So let's see. And thanks for listening again.
Okay. Mm-hmm. So if you have time, I have also a few comments which are quite similar to what Benzo just said. So I think, yeah, understanding stories require you to first identify the characters like you did, but also like Denzoja mentioned, there is this evolving interactions between these characters. I think that's also could be a quite good addition to your speech synthesis part. Like, for example, the characters may be friends at first, but towards the end, maybe they could be menaces. And to include like using different intonations to speech to like give this type of extra information. Or maybe even you can track the places, add some background noise that would really increase the interactive experience.
That's a very good point. Actually, one of the hardest challenges that we've featured is like at the moment we're trying to solve some problems of reflecting voices like coughing or like yelling, and throughout the story a person can get ill, or I don't know, like can graduate from university. Like you know, like the situation might change a lot. And as you mentioned, yes, voice or tone is one parameter that can change, and also the interaction between those characters. Yes, we're pretty aware of them, and it directly affects emotions, and it also affects the character part as well. I think the best thing to do is to shortlist all those potential problems and organize them into maybe a simple ontology, and then prioritize them, and afterwards attack the most attractive. Yeah.
Okay, thank you, Ömer Hocam. Are there any other questions, comments?
So one more before we let him go. So one of the most challenging issues is data, of course. You know, collecting this data, annotating this data in a way that actually annotators can agree on. These are very, very challenging things. I mean, maybe for example, character identification or, you know, dialogue, character mapping, I expect you would have higher inter-annotator agreement, but as we discussed in your last talk, for emotion identification, the agreement is going to be a lot more difficult to come by. So I'm constantly thinking of how can we get around this problem, and can we use any self-supervised techniques or weak supervision? You know, somehow can we get some labels without involving humans when we're trying to do these types of story understanding tasks? So have you guys tried such approaches, semi-supervised or weakly supervised, and what have you in your experience?
Yeah. So we were supervising a student from UCL with Furkan, and he was a Turkish citizen, but I think he's also native in English. That's the reason why we let him to annotate some part of the data. So like, this is the problem of annotating long form documents. So that's a huge separate problem. And I think I mentioned you previously, Deniz Hoca. So even like in correcting the outcome of audio that we produce, we never hire people who are non-native. So because like I'm not sure if we have any native in this meeting, but it's almost impossible for us to detect the nuances in the generated audio. I doubt if it will be the same when it comes to processing the long form documents, but it might be. So we're expecting, like for character identification problem, we're expecting people to read the whole document, invest some time, invest more time than they invest into some other downstream tasks, and to list them, to list out the characters. I say that's one thing. So dynamics are different. I think we have some sources, but we're in the process of how to spare those sources to, like, we will definitely have invest some time, some resources to annotate, because there's a lack of data. When it comes to your point of self-supervised approaches, I think we recently discussed that we can process the scripts, so like scripts from movies, so there should be that kind of tactics or heuristics that we can apply.
So to explain that to people who weren't in that conversation, we were throwing around some ideas, and one idea was theater or movie scripts sometimes contain explicit instructions for the actor to express certain emotions and stuff. And you know, we could take that as the supervision for emotion detection, for example.
I think that would definitely matter. But I would say I would invest like 60-40% or half and half. Half of our resources into the supervised approaches and half the other ones. Let's say, like, we're sort of experienced in designing, developing self-supervised methods from my PhD days. Maybe they will perform better. Like, I don't know. Let's see.
Thank you, and sorry for hugging the question time.
Thank you, Ömer Hocam.
Thank you very much for listening, and again, I hope to be in touch with all of you.
Yeah, so Aykut and I will email you about our next story understanding meeting, and maybe we can just have a brainstorming session on you know, types of problems that would be of interest for you and for our students as well.
That would be great. Meanwhile, I think I got contacted with the department's relevant person who is inviting guest speakers. So we might, in the next one, we might invite like a few of you to give guest lectures or speeches in our department as well. It will be an honor for us.
Thanks. Okay. See you, everyone.
Very much.
Thank you, Ömer. Bye-bye.
Bye.
Bye.